Welcome back. This video is part B of concept of section 11.8, which is about power series. Earlier we saw an example uh, of a power series for what values of x the power series converged. This problem was done example number 1. We also defined what a power series was. Now in this one, we are going to take another example. For what values of x, that's the series sigma, n varying from 1 through infinity, x minus 3 to the power n over n converge. So let's consider step 1. We are definitely going to apply the ratio test. So we'll start with an. An is the given series without the sigma. This is an. So it is x minus 3 to the power n divided by n. A sub n plus 1 is obtained by changing the n to n plus 1 or substituting, replacing n by n plus 1. Now you divide one by the other for the ratio test. An plus 1 over an, which is x minus 3 to the power n plus 1 over n plus 1. Then you flip and multiply n divided by x minus 3 to the power n. You notice here, we can cross out. This will be just x minus 3. So we get n over n plus 1 times x minus 3. Now we have to take the limit and take the absolute value. Here we have to definitely take the absolute value because it involves the x. In the part where you have n over n plus 1, whether you put the absolute sign or not doesn't matter because it's always going to be positive. N is going to be positive. But wherever you get x or x minus 3 or x minus a number, then you have to put the absolute sign. So we will now consider an plus 1 over an. Then we are going to take the limit. So it is n over n plus 1 times absolute x minus 3. If you allow n to approach infinity, that is limit as n approaching infinity of these things, n over n plus 1 divided by absolute x minus 3. Because we are allowing n to approach infinity, we're going to divide the numerator and the denominator by n. And this will become limit as n approaching infinity, 1 divided by this n over n, this will be 1 plus 1 over n times absolute x minus 3, and 1 over n approaches 0. So this whole part the first part will be just 1. So it is just absolute x minus 3 as n approaching infinity. So according to ratio test, when absolute x minus 3 is less than 1, the series would be absolutely convergent. So the given series sigma an is absolutely convergent and hence convergent and therefore convergent whenever the limit L, whenever this limit L is less than 1. So whenever absolute x minus 3, that is the limit in this case, the limit L is absolute x minus 3 should be less than 1. And it diverges whenever absolute x minus 3 is more than 1. And when the limit is equal to 1 though, the test fails. So what do we mean by absolute x minus 3? Let's analyze what we have just found out. Absolute x minus 3 less than 1 would mean minus 1 less than x minus 3 less than 1 by property of inequality. So if you add 3 to all the sides, you get x lying between 1 plus 3, that will be a 4, negative 1 plus 3, that will be a 2. So when x lies between 2 and 3, 2 and 4, definitely the series converges. So the given series converges when x lies between 2 and 4. And it diverges outside of this interval. Diverges when x is smaller than 2, when x is smaller than 2, or x is more than 4. In other words, when in this scenario, where it diverges when absolute x minus 3 is more than 1, which is same as writing x is less than 2 or more than 4. This ratio test is inconclusive when L equal to 1. So what happens when L equal to 1? What happens when L equal to 1? Or when absolute x minus 3 is equal to 1. This means x minus 3 equal to 1 or x minus 3 equal to negative 1. So x minus 3 equal to 1 will mean x equal to 4 or x equal to 2 at the endpoints of the interval 2 to 4. So actually what we have to do, this is a separate problem kind of. We have to discuss the case when x equal to 4 and x equal to 2. Right now we know that in this interval between 2 and 4, the series definitely converges. Then we don't know what happens at x equal to 4 or at x equal to 2. But outside of 2 to 4, it diverges. So step 5, let me make room here. Step 5, check the convergence at the endpoints. At x equal to 2 and x equal to 4. So the given series is sigma an, which is sigma x minus 3 to the power n divided by n. So when you substitute x equal to 2, when you substitute x equal to 2 here, the series sigma n varying from 1 to infinity an becomes sigma n varying from 1 through infinity 2 minus 3 to the power n divided by n, which is sigma negative 1 to the power n over n. Does this series look familiar? So when we did conditional convergence, we referred to this example. This is an alternating harmonic series. Alternating harmonic series, which is convergent by alternating series test, which is convergent by alternating series test. We have proved this. Refer to the notes that what we have done, how we have proved this series, alternating harmonic series, is convergent by alternating series test. So we have picked one number where it is convergent. Now we have to see what happens at x equal to 4. So now you substitute x equal to 4. Substitute x equal to 4 into the series. So we get sigma an, which is sigma x minus 3 to the power n over n, which is sigma. You're substituting x equal to 4. You're substituting x equal to 4. So it is 4 minus 3 to the power n, which is 1 to the power n. So 1 divided by n, which is a harmonic series, or you can say p series with p equal to 1, which is harmonic and therefore divergent. Divergent. So what have we shown in all these steps? The series given in the problem, which is sigma x minus 3 to the power n over n, converges in the interval 2 through 4. It converges at x equal to 2. It converges at x equal to 2. Also, and at x equal to 4, it diverges. At x equal to 4, it diverges. And outside of the interval, at x equal to 4, it diverges. Also, it diverges when x is less than 2 or greater than 4. So we can say that the series converges in the interval 2 to 4, inclusive of 2 but exclusive of 4. So whenever you do these kinds of problems, so one caution is that you will be able to do the first part without any difficulty, but remember that you have to also check the endpoints of the interval because the limit value equal to 1 means that the test is inconclusive. So you have to apply a different technique to find whether the series converges at the endpoints, converges at the endpoints of the interval also. So see you for my in part C of the video for this section.